We will see hardware components related to this instruction execution. Whenever you are executing instruction, then what are the things you require? One is register file, correct? That means set of registers, CPU registers, you know, right? Maybe 32, 64, whatever. Now control circuit. So this is very important. This control circuit is going to generate signals appropriately so that at appropriate time, right action will be performed. We will see that how this control circuit can be designed. That is the major goal of this this chapter, I can say. Now instruction register, because whenever you have a instruction that is initially in memory, right, then we have to fetch that into instruction register. Remember one thing, always we are bringing that instruction into instruction register and we are going to process. That means how do you know that we have to do addition or subtraction, otherwise load? For that we have to decode it. So that decoding and everything will take place after keeping the instruction into instruction register. So once you keep your instruction in instruction register, this control circuit is going to process it. We will see that. Now register file is done, control circuit is done, instruction register is done. So what is ALU? Why we require ALU? You know that, right? So we'll be doing addition, subtraction, multiplication, divisions, right? Left shift, right shift, arithmetic shift, everything. For every such operation is performed using some circuitry. So that entire unit let us call ALU, okay? Arithmetic logic unit. Now instruction address generator. So instruction address generator is a big circuit. So we will talk about this one now. So why it is required? Example, when you have started executing your program, then maybe first instruction, after that we have to go to second, after that third, right? Sometimes what happens, because of the logic in the program, because of the some special instruction like jump instruction, otherwise function call, we have to change the program counter value to something else rather than linear, correct? So generally when your instruction starts at 100, let's say after that 104, then we execute 108th instruction, after that instruction at 112, so on. Suddenly we go to 500 because of so many things. One is maybe it's a function call, right? Otherwise if there is a branch instruction, right, already we have discussed that because of branch instruction, then we will go to some other part of the control, otherwise some other part of the instructions. For that, finally this program counter is going to be modified. Okay, initially let's say program counter is having 120, then because of the instruction, maybe you might have this kind of instruction, branch to an instruction 200. See this instruction, branch to 200. That means so whenever this instruction is executed, then this 120 should be changed to 200. Who will do that? Correct? There should be circuit. So that is nothing but instruction address generator. So finally the story is all about executing the instructions one by one, but where is the next instruction? Maybe sometimes when you are at 120, the next instruction might be at 124 or 200. That is decided by the pure logic of the program. So that's why instruction address generator is going to understand the instructions, current instructions, and it is going to change the program counter appropriately. So we will see that part, like how instruction address generator is going to consider various possible addressings. Okay, now the last one, processor memory interface. If you see, we have load instruction, store instruction, add, everything. So we have, sometimes we have to visit the memory, correct? So whenever you want to visit the memory, then there should be some circuitry, that is processor memory interface. How this can be understood, I will tell you. So you have a memory, okay? So there is a person, for him, so you are here now. This is the memory. Okay, I am talking about this person. Let's say call him Raju. Now, example, let's say you have some address called 200 in program counter. Now, just simply give that 200 to Raju. Raju, I am giving you an address. I want content of the 200. Okay, so Raju is going to, Raju is going to that appropriate memory location 200, and he will fetch the data and he will give that data in some other register. Okay, let us call it as data register. Okay, now what are you doing? You are providing some address in some address register. Okay, let's say, and we are communicating with Raju. Raju, take this address and give the data. So this is the data register in which you have to keep the data. That's it. I will be very happy if you do that. For that, Raju, what Raju is going to do? He is going to that memory and he is fetching the data, correct? So for that it's just, you know, you're understanding it like a person, right? But it is not, actually he is not person. There should be a circuitry, correct? So that circuit should take care of all such things. What are the things? Given address, he should fetch the data. Second one, given, sometimes I give address and data like this, 5000 is the data. Then I call this Raju and say, Raju, this is the address 200, go there and write this 5000. Then he should go to 200 and he should write 5000. Such a circuit I want, right? Sometimes it is needed, right? Majority of the instruction execution is nothing but doing this stuff. That's why we have a separate circuitry that is called processor memory interface. Finally, these are the essential things. CPU registers required, control circuit required, and ALU and instruction register, instruction address generator, and processor memory interface. So using these, only these, I can say hardware, we will be executing our instructions. We will see more details of how an instruction can be executed. Okay. Now before that, I would like to tell you one thing. Whatever may be the circuitry, this is a major circuitry, right? Now question number 1 is how to design it. That means finally what is our goal? We have instruction that should be executed. So that instruction execution can be divided into, that means how to understand that instruction execution is, we can divide that into some operations, right? Correct? So every instruction execution can be seen as doing some small operations, okay? Operations. We will be seeing that operations one by one. Okay. Example, in addition, what are the operations? Fetch the instruction. I am talking about add instruction. Fetch the instruction. Once you fetch the instruction, next you have to understand that decoding. Then third operation is what? Execution, right? So all that operations we are going to do with this circuitry. Okay, we will see that. But the design part I am talking about now, we can design that in two ways. One is, you know, multi-stage, single stage. So finally you realize that to execute your instruction you need some machinery. That machinery can be designed into two ways. One is single stage, second one multi stages. Okay, sir, why multi stages are required? I will tell you. First of all, we'll focus on single stage machinery. Now we'll see one example, and you know, we talk about this machinery properties. Okay, example, you have a instruction load R1 comma something 5000. When you have this kind of instruction, to execute it, we can design the circuitry in two ways. One is single stage, second one multi-stage. Let us talk about pros and cons of the single stage and multi-stage machines. Okay. So in single stage machine, what is going to happen is you will be having a circuit that is going to take your instruction I1. Let's say, let us call it as I1. Okay. When you give that I1 to this machine instruction, otherwise circuit, sorry, then what is going to happen is the desired task. We know what is desired task, right? That desired task is going to be performed. Okay, desired task in one single stage. That means for that we directly give the input and you get the output. So I don't know how many clock cycles it requires, maybe 2 clock cycles or 1 clock cycle. Maybe you can do it in 1 clock cycle. Sir, how can you do, you know, this much big task in 1 clock cycle? Yes, we can do. Simple, because we can extend the length of the clock cycle. Example, let's say the duration of clock is 1 microsecond, just for time being, you know, assumption. Okay, so if within 1 microsecond, if this circuit won't stabilize, that means this circuit cannot compute all the things which are required in this operation or instruction, then what we do is we take a bigger clock. That's it. Take a big clock like this, 2 microsecond. Fix the clock to 2 microsecond. If it is not sufficient, go to 3 microsecond. That's it. In that way, so we can design a circuit which can execute this instruction in 1 clock cycle. Okay, so that is single stage machine. Now we can have another concept called multi-stage machine. So multi-stage circuit. In multi-stage circuit, what are we going to do is we are going to execute this instruction in multiple phases. Okay, so let us take one case called 3-stage machine. Okay, in 3-stage machine, what we are going to do is, let us, this is stage 1, this is stage 2, This is stage 3. Okay. Now you have lot of registers. I will tell you. This is called register. Why we require registers in between stages? I am going to explain you. So this is called multi-stage circuit. So I am dividing the work of that instruction execute into some parts. Okay. So finally, executing this instruction, first of all we have to fetch it, right? So I do fetching here, maybe. Then I decode here and I execute. In that way, I divide the work into 3 parts. So here maybe, so here some input will be given, right, in this register. To fetch the instruction, what you require? Program counter. Maybe the program counter is, stored in this register. Try to understand in high level, don't go into, details. So slowly we will try to understand it, okay. Now, these registers are going to be used to store the information which is required to fetch operation. Before fetching, what you want? Address of the instruction that will be provided in this register. Okay. Now fetch it. Once you fetch it, that instruction will be, so here I am doing decoding, right? To do decoding, Mr. Decode, what do you need? I want instruction. Okay. So this fetch is fetching the instruction, right? So here once that instruction is fetched, that will be, let's call it as I1. That instruction will be, temporarily stored in this register, so that can be used as input to the decode circuit, correct? Now that instruction, which one, I1, is taken as input by decode circuit, and that is going to provide some output. What is that output? That output, that's a separate story. What is the output of decode is understanding the instruction, that it is load, right? And issuing different kind of control signals. We will see that. So far, we don't know like how to generate the control signals, everything. Finally, the goal of decoding is nothing but understanding the operation. Okay. Now once it understands the operation, it will see that, because since it is load, right? So for loading, what you require? Maybe memory address. We have to go for memory address, right? So that's why. So next phase is execution. This decode step will gather all the information which is required for execution phase, and it will supply. Maybe execution phase require memory address 5000, because this execution phase should go to memory. That's why where to go in memory? 5000. That will be supplied by decoding. Okay. In that way, these stages are going to help each other, right? Stage 1 helps stage 2. Stage 2 helps stage 3 through the buffers. Okay. In that way. So these buffers are going to help in forwarding the data to the next stages, right? So that is what the idea of multi-stage circuit. But sir, why we have to do the things in multi-stages? I will tell you, there is a concept called pipelining. So in pipelining, whenever your operations, otherwise it's a task or work, this is instruction. Executing instruction is a work. Okay. So whenever the work is distributed into multiple stages, then pipelining is going to give us an advantage. Then we can have parallel execution. That's why we will be studying pipelining in very detail. At this moment, you remember one thing: whenever you have some work, that means here executing the instruction, if I can divide that into some stages or some distributed works like this, that means if I divide the work into multiple parts, then we are going to get the benefit in pipelining. That's why we will be converting it into multi-stage problem. Okay. Now while designing the circuit itself, we will be designing it such a way that circuitry will be divided into stages. That is what I would like to say, rather than single stage. In the single stage, all the circuit will be messed up, and there will be only one stage, and input will be instruction, output will be what is the output? Executing that, correct? But in multi-stage, we divide the work into systematically into multiple parts, and we'll see one by one. We'll do one by one. Okay. So in real life, we have such kind of things. Example, let's say some people like, car manufacturing. While manufacturing the car, the work will be actually divided into multiple parts. Okay. Someone creates engine, someone will design. Remember one thing, example, you want to create a new car. Designer will be someone like, the engineer, correct? Who is going to design the car model, everything, right? Now second part, manufacturing will be different. Some other people will do the manufacturing, right? So in that way, maybe coloring. Who will do the painting? Engineer? No. Correct? Who will do that? some other specialist. In that way, we divide, or creating the car is divided into multiple parts, correct? So for everything there can be a specialist, rather than, imagine this one. Let's say you are creating a car, or you are designing a car. Finally, you want to have a end-to-end functionality. That means you want to create a new car. Then first we have to design it. Then after that we have to, assemble it, right? We have to create all the parts. Then after that we have to assemble it. Then we have to paint it. Correct. We have to advertise it. If you do everything, then definitely, is it not awkward? Yes. At least, advertising part definitely cannot be done by engineers, right? That's why some management people should be there. In that way, so always if you divide the work into multiple parts, then you get benefits, right? Similarly here also, so that we will be seeing in pipelining, we will be getting the benefits. That's why the functionality we will be dividing into, stages. We will see that stages, how many stages are required. If you want to ask, then ask me. That, the answer is very simple. The number of stages depends on the experience. Like, we will see that. For that you should understand the instructions carefully. What I do is, I show you all different instructions, and we'll try to understand what is the meaning of each and every instruction. To execute that instruction, what we have to do. Then after that we'll come to number of stages. Okay, we'll identify that. Let's postpone the number of stages problem now. Now we are going to understand, first of all, each and every type of instruction, like load, store, add, everything, and we'll be closely observing what are the things are going to happen in that instructions. Okay, now to understand how many stages we require, okay, in the circuit, first we try to understand load instruction. Like, what are the operations, small operations we have in, okay, that load instruction. If you see load instruction, example, load R5 x of R7. I'm using indexed addressing mode. Okay, so in indexed addressing mode, what are we going to do? How to understand this instruction? We first of all forget about that time, how to do it. First of all, the very important step is we have to fetch the instruction, isn't it? So that is clear. Fetch the instruction. After that, understand it. Correct. Before that, increment the program counter. Correct. Because once this is done, maybe if it is, not a branch instruction, otherwise not a function call, the next instruction to be executed is definitely after this one, right? That's why increment the program counter is the second step. Let us do that. Fine. Then the third step, understanding it. You see, decode the instruction to determine the operation. Yes, we decode it. Then fourth step, add the immediate value x to the contents of R7. We know the execution model, right? So what we are going to do is, in this load R5 x of R7, x plus R7 will be computed, correct? That means the content of R7 is added to x, then you get some value. So we will be going to that memory address. Example, R7's content is 100, then x is, let's say, 200. 200 plus 100, 300. Go to memory address 300 and fetch the data. That means fetch the data and store it in R5. That is what the operation, right? So I can systematically write like this. Not a big deal, right? So third step is understood. Fourth step is add the immediate value. This is immediate value, right? X. Correct? That immediate value we have to add to content of R7. Why we say immediate? Because so in the instruction itself, this value is represented, but 100 is not represented in instruction. What is represented in instruction? Register address, R7's address. Then we have to go to that address, then we will get content. That's why I can say that x is immediate but not R7, right? Now, so that's why add the immediate value x to the contents of R7. We know that the fifth step is use the sum x plus R7. Yes, I use that as the effective address. Yes, now 300 is the effective address for what? Operand. Address of the source operand, and read the contents of that operand. Yes, I do that. Then last step is what? Once you read that operand, you store it in R5, right? Load the data received from the memory into the destination register R5. So there are 6 operations. Now these 6 operations, if you closely observe, we can, write them into 5 major parts. You see them, okay? Sir, how do you know that we can write them into 5 parts, not 4 parts or 3 parts? It comes by experience. Okay, so already that architecture people who are experienced, okay, so since hundreds of years they are creating new systems, and they realize that So especially for this kind of risk kind of instructions, the best way of designing is 5 parts. Just understand it, like, example, let's say really I'm dividing this entire work into 5 parts. How it looks like we will see. Okay, slowly you will realize that, and you will be convinced that it is really good to design our operations. Otherwise, the all operations of this load instruction into 5 parts. Why? When will you realize it is after learning store operation and add operation, everything. First of all, just understand what are that 5 operations. Again, one more time. Okay, first step is fetch the instruction. Correct, we do that. Here also we did the same thing. Then increment the program counter. So that means 1 and 2 are merged in one way. Okay, so finally in one step you do this one, fetching the instruction and incrementing the program counter. In the second step, what you do is decode the instruction and read the contents of register R7 in the register file. Okay, see here, what are we doing here? Decode the instruction and understand it. At the same time, read the contents of R7. That we can do in second step. Now third step, you see, in the third step, compute the effective address. How to compute the effective address? Recall, example, already you read the value which is in R7, which is 100. Now I want to compute the effective address. What to do? Already this x value is available with instruction itself, correct? Because whenever instruction is given, where we are storing it? When you fetch the instruction, we will be fetching it into instruction register, right? So in the instruction register already we have x value 200. Now take this 200 and take this 100 and add them. Then you get effective address. For that, here we have to use adder circuit. In the third step, we will be using adder circuit. Sir, where is the circuit? We will see that circuitry part later. First we understand how to divide the entire work into 5 steps. Okay, so compute the effective address. Yes, using the arithmetic logic unit we can do it. If you observe one thing, so far we have not at all used any addition subtractions, right? So in the third step we are doing arithmetic, remember it. So in the first step we are fetching, in the second step we are understanding the instruction, and at the same time we are reading the data from register 7. Now fourth step, read the memory source operands. Okay, read the memory source operand. That means we will be storing, did you remember? Let me write the instruction here. Load R5 x of R7. Finally, we have to get the data and we have to store it in R5, correct? Now after third step, what is available? Address is available, right? Where to go? Now in the fourth step, go to the memory and prepare the source operand. That means get the data from that. So read the memory to get the source operand. Yes, I do that. In the fifth step, what we do is, load the operand into destination register R5. Correct? Because already we got the data. Now we will be storing it into R5. In that way, we can imagine our instructions execution into 5 parts. Here execution means from scratch. Fetch it, decode it, do the remaining things, execute. So execution we are doing into 3 parts, right? Into 3 steps. So this entire thing is, I can say, a 5-stage design, correct? Or 5-stage design. So, sir, why are you using 5 stages? Still we are not convinced. You will be convinced only if you understand other instructions. Now similarly, we'll observe the next instruction, which is add instruction. Okay. Now